Interpreting sinusoidals, Unit 6, Lesson 3, Question 1. Two weights attached to the end of two springs are bouncing up and down. As they bounce, their height in centimeter varies with time in seconds, as shown in the graph. So as you can see, one of the coils are going like this. It's like a skinny kind of wave, while the other one is like it has a longer wave, and it takes longer for one period to occur. So I took some images of like a skinny coil versus a large coil, and then try to think out which one probably goes with which. So before I interpret that, I'm going to try to see what's going on with the numbers. So for example, this graph has a single cycle that ends here. It resembles a sinusoidal because it starts here at the axis, goes up, and then comes back at the axis. So this graph has a max at 80 and a min at 20. The axis is occurring approximately at y equals 50. The period of a single period for this one cycle is, we're seeing that it's 1 second. So one period is 1 second, meaning for it to go back to its original position of where it started from and how it makes that one cycle, it takes 1 second. For the other curve, it coils like this. It starts at the top and then comes back to the top, right? So that resembles a cosine graph, okay? So that's how I know when and where I want my graph to end. I noticed that 60 is the max and 40 is the minimum, where the axis is still occurring at y equals 50. Unlike the first one, we have a period that is different. So we have a period that is 3 seconds. So think about how a coil works. If you have a skinny coil, right, it's going to bounce rapidly. Think about it if you are you had one of those shoes with like the springs. If it's very skinny springs, it's going to go up and down really fast. That's how one way to think about it. But whereas when I anticipate like a large, long coil with a larger radius, it's going to be more stable and it's going to go more slowly as it opens up, and then it becomes skinny again. So with that in mind, I went and tried to number our graphs. Meaning what I assumed was, well, if I call this a skinny coil and this is the wider coil, that this yellow graph is likely the skinny coil, and then the wide coil is more likely this. From there on, you can start writing your similarities and differences because they ask you to compare and contrast the bounces of these weights and how they differ and how are they the same. So just wanted to point something out between the skinny coil versus the wide coil. So it is, at the end of the day, based on the material that determines the stiffness of the material that will determine how it's going to bounce, right? And the pictures I kind of chose kind of resemble that the skinny coil will likely bounce really quickly up and down, whereas the wide coil will be very subtle as it's going up and down. So just keep that in mind. Skinny coil versus wide coil, at the end of the day, is one way I was labeling the graph. So with that in mind, I concluded that the wide coil will take longer to return to its original position based on its material and perhaps the radius of the coil. So let's look at some of the similarities and differences. So for instance, skinny coil versus the wide coil, you notice that you have like a consistent radius throughout. So you're having this sinusoidal periodic function where the oscillation is consistent. It's not like decreasing in size as time goes by, because it's not a coil where it changes in its radius size. So I noticed that is one similarity between the two. Another thing to note is that with these two graphs, you notice that the axis value is exactly the same with y equals 50. Remember, this y-axis represented their bounce in height in centimeters, which means that at t equals 0 second, at its original position. So interestingly enough, although we're starting at different positions, we're noticing that the axis value is y equals 50. And what does that mean? What it means is that the mean value, the part when this coil is becoming really tall and really short as it's going up and down, its mean average is going to be at 50, which means at rest position for these two coils, they're both going to have a height of 50 centimeters. So another similarity that we can add is that at rest, both coils will be 50 centimeters tall, and that's because the axis is y is equal to 50 centimeters. Let's look at some of the differences. So let's look at this skinny coil, I guess, the yellow one. And we notice that it basically reaches a max height of 80 and then a minimum height of 20. Another thing we can note is that we already wrote that at the beginning, but it would take 1 second for it to start at its original position, reach its max height, and then coil down to its original spot, get really short, and then come back to its original position. That cycle is going to take 1 period. In terms of the Y coil, it reaches a max height of 60, and then it has an average of 50 as the height. It reaches a minimum of 40, so it has a max height of 60 and min height of 40. So with the coil, it's relative to when the timer is started, and so keep in mind in this case, the coil actually starts at its max height, which resembles the cosine graph, and then hits its minimal height and then comes back up. So these are some differences that we notice, whereas for the other coil, rather than it taking 1 second for an entire period, it takes 3 seconds for a single period to occur. So that is all for this example. So transform function. Recall that you have the f at x. F is the name of the function, x is the input. When you have a transform function, you're going to have things like vertical stretch, horizontal compression, vertical shift left, horizontal shift left or right, and then vertical shift up or down. So with that in mind, what does the A mean? So when you have a vertical stretch, we say that the A value, the absolute value of A is larger than 1. What does that look like? Well, if you have a graph, like a parabola like this, when you have a vertical stretch, we're thinking this way. And this way you're stretching it, and so then it's going to become skinnier. That's what a vertical stretch means. Whereas for a compression, well, if you have this graph like this, if there's a vertical compression, the A value must be between 0 and 1. Or it could be less than 1 as long as you're talking about the absolute values. And if you have a vertical compression, that means you're actually having like a wider graph, because you are, instead of pulling it this way, you're like letting it loose, and so it's becoming wider vertically. Next, keep in mind that when you have a graph like this with the parabola, if the A value is negative, what's going to happen is that all the Y values are going to switch over, and therefore then you're going to have a graph that looks like this, which means when you look at it in terms of the XY axis, you've had a reflection along the X axis. For the K value, so K value is when you have this is how I remember it. You have your parabola, right? And This time you have a horizontal compression. When you have a horizontal compression, that means you're getting wider this way. And when it's becoming wider, that is that the K value is also becoming larger than 1. Okay, so that is the go-to. So horizontal compression, you're going to be able to see that when the K value is larger 1, and you're going to factor the K out to make that happen. Meanwhile, when you have a horizontal stretch, well, if you have a graph like this, if you're now pulling it this way, now you have a wider graph. And just like you had in this case with the vertical compression, when you have a horizontal stretch, you're going to also have a wider graph. And you're going to have a horizontal stretch and vertical compression. Those are comparable, while the vertical stretch and the vertical compression is comparable. So I'll just highlight, like, this is my go-to and this is my go-to, meaning I usually am dealing with A values or K values that's larger than 1, usually not a fraction value between 0 to 1. And that's what I mean by it's my go-to. But when I do see that the values are in fact a decimal and less than 1, then I can say it's going to be a vertical compression or horizontal stretch instead. So when you have a graph like this and you're dealing with some horizontal movements, so whether it's horizontal stretch or horizontal compression, things are changing along this way, right? That means that with the X and Y axis, what's going on is that you're actually having a reflection along the Y axis every time you are dealing with the K value. And therefore, you're going to have a reflection in the Y axis when K value is less than 0. For the D value, this is the shift left or right. So you have to make sure that the K is again factored out to be able to see that. And that's what I've written. And you got to make sure you're switching the sign. Meaning, if it says X minus 2, it says minus 2, you're going to switch the sign and make sure you write D equals 2 when you see X minus 2, because there's already a negative within the equation, and so you're not going to grab that negative with it. You're simply going to grab that D. If it says X plus 2, well, the equation includes the negative, so then you're going to switch the sign and grab the opposite sign. In this case, you would write D equals negative 2. I love this laser thing. And then the C is it's pretty straightforward actually. You're either going up or down, and that's all there is to it. And it shifts up or down. So hopefully you've seen me draw these a numerous number of times, and you are also starting to become comfortable with it, but it definitely does take some time. I usually draw the 4 lines to indicate that I want 5 coordinates. I start off at the beginning and then I end at the end. I know there's one in the middle. It might help to write, okay, so sine x I know goes a full circle and it's 360 degrees for the period. That makes this 180, 90, 270. I know that if it's a positive y equals sine x, which is like the parent graph, it's going to hit the max first and then it's going to hit the minimum later on. And so it's going to go up, meets the axis, and then goes down to the minimum and reaches the axis. So y equals sine x. And then the parent graph is Again, the same idea. You have this exact same max or min. You have the same period for cos x versus sine x. The only difference is instead of starting at the axis, I'm going to start off at the max. And if you compare the two and you kind of look at it like this, see how I'm looking at it like that? I'm really kind of just continuing it on. So I go to the axis next, the minimum, the axis, and then to the max. It's like I had to continue so that it would look like this, so it looks like a full period. So yeah, they are very interchangeable. and there's your cosec's. So the reason I need to bring this up is I need to give you some tips on how to use transformation features to graph sinusoidal. I find that it is a lot actually easier to graph sinusoidal once you really get this down. And I actually use this versus this transformation features when graphing sinusoidals. You'll see in a minute maybe why that is. So for example, let's start out with finding the range. When you're finding the range, well, what are you interested in? Well, your graph goes like this, right? And that basically means that you're hitting a max and you're hitting a min. And so and I think we've seen that before, that you're going from min and you're going to max. And hopefully that part is straightforward. We need to move on from here. So one part I'm going to add is that the C is equal to the axis. Well, what does that mean for a second? Well, for example, right here, the axis was 0. Axis was 0, meaning the y mean value was at 0. It was oscillating around that y value of 0. There was no shift up or down to any of these parent functions. And so I could comfortably say that the axis is just C in this case, which was 0. But as soon as I add plus 2 to it, what's going to happen is, well, I'm only going to go up 2, and then I'm going to have my graph accordingly. Well, we're still going to go about that axis, and so we're going to explicitly say that C is equal to the axis. Another part I'm going to tell you is that when you have the A value of your transformed equation, the A bar part actually tells you the amplitude. So how far are you from the axis to the maximum? And this will make more sense as we go through an actual transform function. But in terms of how we can see it here, well, obviously the value that the sine x and cos x both multiply is simply 1. And you notice that the amplitude is actually 1 as well. So there is some correlation to it. Let's go from there. We have our minimum. Well, how do you find your minimum? Well, once you have these two information, it becomes a lot easier. Well, how do you find your minimum? Well, if you have your axis and you subtract it by the amplitude, you're going to be able to figure out your minimum. I.e., if you have an axis of 0 and you subtract the amplitude value of 1, you're now at -1. So could you guess what's going to happen for the maximum? Well, you're going to start off at the axis. You're going to add the amplitude. And so what's going to happen is that you have an axis value of 0 and you add 1 to it, and that's what you have. Next, this is probably the most helpful one. When you are looking for the K, there's an equation associated with it, and it is 360, which is the regular period of the sine x or cox, right? Cosec. And what you're going to do is, in order to find K, you're going to divide it by the period of this new function, and you're going to be able to get the K. Well, algebraically looking at this for a second, well, how do you solve for P, and what if I know K this time? Well, what you're going to do is you're going to do P is equal to 360 divided by K. And why is that, and how did that work? Well, simply by cross multiplying and switching its spots. So I won't show that, but these are the two versions to work with getting the K or the P. So that is the same. Let's go on from here. So what about the domain? I did the range right away. So with the domain, well, unlike some functions like the rational function where you had a restriction because there was like a vertical asymptote, there's a horizontal asymptote. Or let's say like the square root function where you couldn't take the square root of a negative. There's not really any restrictions with the sin x or the cos x. And so we are simply going to write down d is equal to x elements of real. But at the same time, it's not as easy as that. Meaning that if you have like one cycle, that's 360, but you have to know what the domain is. If I said, okay, what about for 2 cycles? And then keep in mind there's shifts, the left-right shifts associated with it. So you have to know what the big picture is and be able to figure out what the period is with regarding to the question, because usually it's going to specify it by how many cycles, and you have to know how to deal with that. And so one way is if let's say they want a specific number of cycles. So example, if they ask for 3 cycles, and as long as I assume that it starts at 0 and you're simply adding the periods, well, if that's 1 cycle and you want it for 3 cycles and it does start at 0, then you're going to simply do 3 times p because that's how many it takes for 3 cycles. 3 cycles are going to be 3 periods, and so you're going to say that the domain is equal to x elements of reals such that it's between 0 and 3p, where you have to actually put in what the period is. So some other thing to keep in mind, it might be like the non-official ones that you could keep in mind, just because it won't work all the time, because you have to have like a thorough understanding of what's going on with the graph. Like, is there a reflection? Is there not? But this does help to kind of get the ball rolling on how to graph when there's like a shift, let's say. For example, we said that D was our shift left or right? And so what that means is when you have a graph like this, and if let's say D is equal to 20, then what's going to happen is instead of starting at 0, well, I'm just going to move right 20 and then draw my graph. And so what I can do is use that number as the first x of the coordinate. Again, depending on the graph that you have, this may or may not make sense. Like, what if the number is outside of the domain? And so all of these 2 parts probably won't make sense unless you actually face the scenarios and you can see the usefulness on why I might have written this down. But for now, I'll write it for your notes, and I'll write, okay, I can use D as x of first coordinate of a cycle. Well, rule of thumb, I know there's always 5 coordinates involved. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Whenever I'm dealing with sin x or cos x. So another tip I'm going to give you is that if, let's say, I know where it starts, and it's not always going to start at 0 nicely. So what if it starts at 90 and I don't know where to put my next last dot, because that's how I usually draw it. I usually start it from the first and then the last, and I go to my middle, and then I go to the second, and then I go to the fourth. Like, there's an order that makes sense. When there's a shift, what you're going to do is you're going to add the period to the D if I use this method. So, for example, if I did in fact shift by 90, well, I'll do 90 plus 360, and that's equal to 450, and I'll be able to get that last coordinate of that cycle, and then I'll be able to put a number down there, and then there, and there, and now I have magically created a graph that has shifted right by 90. So let's go to draw one cycle of the following. So what I try to do is grab all the information. So that means A is equal to 3. The K is nicely factored out, so I won't have to deal with that per se. So this is K is equal to 4. D is equal to 45, and not just the and not negative 45, c is equal to negative 5. So this is how I interpret it. I try to interpret each part. I usually start off with the axis because that's like my mean. That's where my starting point is, etc., etc. So c equals negative 5. That tells me that is the axis. So basically, axis is equal to y is equal to negative 5. Next, I might go to the amplitude. So a is equal to 3, and because of that, a is the absolute value of a is the amplitude, and so my amplitude is equal to 3. So let's look at our k. So with the k, there's an equation involved, and I remember that it's P is equal to 360 divided by K. So I'm going to plug that in. P is equal to 360 divided by 4. Notice that I'm still in degree mode. So 360 divided by 4 is 90 degrees. So that is my period. The period is 90 degrees. With D equals 45, well, trying to consider what that means. It means that there has been a shift to right by 45 degrees. But what does that mean? Well, I told you that when you look at it that way, it's really like the first x coordinate of a cycle. So that's going to help me out when I'm starting to draw my graph, right? In terms of when I end, well, because I have a shift, I can't just end at 90 anymore. It's not just 0 plus 90. But with that same idea for this question, I'm just going to do D plus P. D is equal to 45 degrees. That's my shift. The period is 90 degrees, and therefore I'm going to end at 135 degrees. Okay, at least with this part, I'm not sure if it works every single time. So when I'm graphing these, I just try to think of if everything that I'm drawing kind of makes sense. You can maybe use Desmos to double check. So these are two things I added to the list that I usually had. Okay, so let's start graphing. When you're graphing, it's really important that you don't start off with like the axis and the values first, but you're basically creating your axis based on all these informations. Because if you have the right axis and the right values, it's going to be a lot easier to graph. Like, I don't want to draw a graph where it's 1, 2, 3, 4, 5 degrees, etc. I want to do it so that it makes sense. So for example, I noticed that I have more values that are negative, so I'm going to draw it like that. I have a slight shift to 45 degrees, so I'm going to start drawing it so that maybe this is 45 degrees. And notice that I want 5 coordinates, and so that means I need 4 lines. And I need to start off by drawing, let's say this is going to be -5. What does that mean? That is my axis. Well, I'm going to go back a bit. What is the amplitude? Well, the amplitude was 3. That means I'm going to try to find my max and min accordingly. So for example, 3 minus 5 is -2. And -5 minus 3, because I want to, I'm thinking about it logically. I'm not too focused on the equation, because once you have that equation down, you kind of want to really write down what is going on, right? Anyways, -5, -3 is -8. So I have my max, min, axis, and quite a lot of information. So we notice that the period is 135, and so we're going to go back and say, well, that's going to be 135 degrees. What I usually do is I'm going to use a calculator, let's say, and you're going to do 45 plus 135. You get, let's say, 180 degrees, and 180 degrees divided by 2 is 90 degrees. So you are kind of going through it step by step. I'm numbering these to tell you what kind of coordinates I'm going to first, what x coordinate I'm going next. And then it makes sense that I'm going to try to get this coordinate and this coordinate. And 45 plus 90 is 135. And then 135 divided by 2. And you can write that number down if you need. Right now I'm doing a sketch. I just want to tell you what the thought process is in getting every single part. I'm going to leave it at that. So next important thing. I always get really, really comfortable with drawing the parent function, because every transform function looks exactly like the parent function, except that the scales are different. I can magically put like 100 and negative 100 there and like 1,000 there and still draw my graph the same like looking, but my equation will be totally different. So what I'm saying is that you can just draw your axis to make it make sense for you. All right. So what is my graph going to look like? I know I want to start off at the axis, hit the max, hit the axis, hit the minimum, and then return to the axis. So what's going to happen is that 45 degree is going to the very first x coordinate. As the next coordinate, I'm going to let it go to the max, return to its axis, go down to its minimum, and return to its axis. And so it's going to look like a nice curve like this. And keep in mind, you could keep going. So I'm noticing that all of my numbers are kind of nice. Like it makes sense. The scales are made sense. So I could actually keep going and draw a coordinate there and coordinate there to show that this is actually what the graph would look like for more than one cycle. So I showed you how the graph can be extended, but because the question specified to just draw for one cycle, I am going to just erase that part so it doesn't confuse you. Oftentimes, though, the question will say to graph for, let's say, domain 0 to a certain number of degrees. They'll usually specify, or they'll usually say draw for 3 cycles or 2 cycles. That is more common rather than just to draw for one cycle.